class, so this section is 11.2. We're going to be looking at Brønsted Lowry acids and bases. This is expanding on the Arrhenius acids and bases, which was too specific and too defined. This gives a more general definition of what an acid and a base is. For instance, for the Arrhenius acids, bases, had to have a hydroxide ion. In this case, we define as different than that. It doesn't have to have a hydroxide ion on it for it to be a base. So Brønsted and Lowry acids and bases are named after Brønsted and Lowry, two people that were independently researching this at the same time, so they both got credit. They did not work together. And according to the definition, an acid is a substance that donates a hydrogen ion, which is the same, it's the same for Arrhenius acid. However, I put in the box corner over there the definition for a base for Arrhenius, and this is a base is a substance that accepts the hydrogen ion. So basically we're following the hydrogen ion, and whichever one accepts it is the base. Whoever transfers it, donates it, is the acid. So think about a ball. Somebody's throwing the ball, that's the acid. Somebody that's catching the ball is the base. So if we look at this compound here, this reaction, we have HCl in the presence of water, and it produces hydronium ion and a chloride ion. Sometimes we show this as a H+, which is by itself. It's not a free ion. However, we remove everything else that's not actually playing a part in the chemical reaction, which is why you'll see it like that. They both mean the same thing. But, so if you looked at the H+, it's just missing the chloride ion. But the chloride ion really isn't playing a part in this at this moment, so that's why you don't see it. But these reactions actually mean the very same thing. So if we look here, first thing you want to do, figure out which is the acid, and then the other one has to be the base in this case. So if we follow the hydrogen, we can see that hydrogen is here with the Cl, but it's not here. So that means that the hydrogen left the chloride. Now this is a one arrow, so this is a forward reaction only, and that's because HCl ends up being a strong acid in water, aqueous solution, and it 100% disassociates, breaks apart, does not come back together again. The attractions toward the water are stronger than the attractions for it to come back together. So in this case, the proton, I call it a proton, many books call this a proton, your book calls it a hydrogen ion, it means the same thing. Why is it a proton? Because H by itself, when it's neutral, has a proton, has an electron. However, we lose the electron, meaning that now we have one proton and 0 electrons. So we have a positive charge because there's nothing to balance it out. So that's why we call it a proton. In this case, the proton hydrogen ion is transferred to the water, and the water takes it on, and now it is a hydronium ion. This is a acidic solution because hydronium ions creates an acidic environment. We're going to expound on this, and we're going to start identifying which is the acid, which is the base pairs. We're eventually in this last section of chapter 11 we'll look at bases and this buffers, and this all comes into play to understand buffers. So this was a one forward reaction only, not a reversible. Now we're looking at a reversible reaction, in a reaction of ammonia and water, and we can see that we have ammonia, and that's going to act as a base. And water now is going to act like an acid where it was a base in this reaction. So the attraction for ammonia has a stronger attraction for that proton hydrogen ion than the water does. So this ends up having ammonia. It's a basic solution, but it ends up having ammonium ion and hydroxide ion. Now I know that the solution here says hydroxide ions, but we're actually we're just following the hydrogens here, not about the hydroxide ions. Okay, so looking at this is an equilibrium reaction. So if you look on one side, you can see that the proton, the hydrogen ion is donated to the product side. So you see ammonia, follow it, now it has ammonium ion, so you can see that the H was transferred here, where here you can see the H is lost with the water. But you can see here's the base, here is the acid, ends up in a basic solution. Okay, so here we need to identify the acid and the base and the reactant. So we're only looking at the reactants, but in this case it's easier to see what's on the product side to determine sometimes it might be confusing about which one is the acid, which is the base. So we have nitric acid. This is a polyatomic ion. You can see that, remember with naming, it is nitric acid because it is nitrate, so the ic acid. And in this case, you can see that the hydrogen was lost from the nitric acid. So that's going to tell me here's the acid. So if this is the acid, this is the base, and the base is the one that accepts the hydrogen. So here's the acid, here's the base. Now if we look down here, we have HF. Let's follow HF. We see that's an ion, so it lost the hydrogen. So here's the acid. That means that this has to be the base. Let's check. Yes, it took the hydrogen. So this is the acid, this is the base. And we are right with that. Okay, so now we're going to look at conjugate acid-base pairs. When we look at reversible reactions, we have two things going on. And there's one pair that occurs in the forward direction and another that occurs in the reverse. So we're pairing up what happens to these compounds. And the best thing to do is determine which is the acid, which is the base. And if it's the acid, then it must have a conjugate base pair, a conjugate base. And if it's a base, it has to have a conjugate acid to it. So if we look here, we can see that this is a very general equation for conjugate acid and base pairs. H is the, of course, that's what we're looking for. The A can be anything. It can be the F, it can be the nitric. It's anything that, this is just general. So here we have HA, and let's follow it. So if this is HA, and this one doesn't have an H in it, so this has got to be the acid, this has got to be the base. So if we look and follow it, we can see that now we have an A minus, which is the anion. So this has to be the acid, this one has to be the conjugate base. So we've figured out one pair, but there's got to be two because we have a reverse and a forward reaction. So now we look at the base, and if this is the base, that means that this has to be the conjugate acid, and it is. So here we have the base, conjugate acid. Why? Because if we go in the reverse reaction, this is now the acid, and this is the base. So in this case, we're looking at a forward, and we're looking at the reverse way, but it's really easy if you just, right from the start, look at which is the acid and the base on this side, and then you can make determinations on the other side. Instead of trying to focus on the reverse and the forward, it's kind of hard to look at that in the beginning when you're first learning about this. So here is an acid-base reaction. We have HF and water, and it produces, in the green box, the fluoride ion, and in the purple is the hydronium. So you can see that the squares are one reaction pair, and the circles are another. So the first thing I say to do, so it doesn't get complicated. First thing, look at the reactants, look at one, and follow it. And see, did it have a hydrogen? Did it not? Follow it. If it ends up being a product without a hydrogen, that is tied to that. So we can see that it lost it. So in here, we look at HF in the red box. That's the acid. Because when we look at the product side, the F doesn't have an H anymore. So we know that this is the acid and the conjugate base pair going forward. Now, make it simple on yourselves. Look at the next reactant. That has to be the base. Follow it. Did it accept a proton? Yes, it did. So we have our base and conjugate acid pairs. The book wants you to look at it in forward and reverse, but when you're first learning it, it's very difficult to see that, and it's you forget the definitions and you can get really confused. So right off, figure out which is the acid, which is the base, and then that will allow you to determine which is the conjugate base, which is the conjugate acid. Focus on one reactant and one product that matches it first, and then look at the other one. I messed up on this page, and I realized it, that this reaction I put here does not match what I wrote up here. So I'm going to fill in what these mean. So in this case, you can see that I put this back up here. We have HF and water. And if you break them apart separately, you can see that this HF donates the hydrogen. It doesn't donate it to the fluoride, but it donates it. It's gone. So we end up with HF and then F minus. And here, this is where the hydrogen went. Started with water, and we end up with hydronium ions. So if you break these up, if you lose the H here, this one has to show the H. So in this case, this would be, and it doesn't matter, honestly, with here, it's just asking for acid-base pairs. So it's not asking for a particular order. We can say HF / F minus. That's how you write the conjugate acid-base pairs. On the other one, as you can see, it's exactly fine. H2O slash H30 plus. So the only one that's wrong here should be HF slash F minus. That's writing a conjugate acid-base pair. Now, if it specifically asks for the acid and conjugate base, then you need to make sure you are specific about which one it is that you would be writing about. Okay, so write the conjugate base for each of the following. What does that mean? For here, we're asking about if this is an acid, what does an acid do? It's going to donate a proton. So we need to break these apart. So we want the conjugate base. Conjugate base means it doesn't have the acid anymore. So we've got to disassociate all of these. One thing I want to make a note of, these are all neutral compounds. When you break these up, they have to have charges on them. Because of the fact that we are breaking them up, they are no longer going to be neutral. Now, this B and C have 2 hydrogens. You will do this in steps. So you will lose 1 hydrogen on each of them. You won't lose 2 at a time. We don't do that. One, like a stepping stone. Loses 1, loses the other. Right now, we're just focusing on 1 hydrogen. So if you draw a line or you make a notation, this has got to break up. And this is going to be H plus, Br minus, and an arrow. That's what you see here. Here, we break up a hydrogen, always has a plus charge. That means that you're going to have to put a charge because it's no longer neutral on here. And that's what we do. So as you can see, break this up. It's now HS minus. So this is hydrosulfuric acid. Simple and non-metal, add the hydro and ic acid in it. Here is carbonic acid. It's a carbonate. This is bicarbonate, so we add, it's called carbonic acid. So in this case, all have an H plus, and then we have an ion that attaches to that or is on the other side of it because these are all no longer neutral because the hydrogen, the proton left, making it more have more electrons than protons on it. So these are the bases. Here are all the bases for the acids. Now, what if we do the opposite? We are going to write the conjugate acid. That means reverse it. We are going to add hydrogens to this. Now, here's a note here. If you look at these on the opposite way, if they end up with charges, they're going to end up with neutral compounds. If there's a neutral compound, it's now going to have a charge by adding a hydrogen, which means you're going to have an imbalance and you're going to have more protons than electrons. So if we take a look here, we add the H's back. Now we have a neutral for this one that started with a charge. This one did not have a charge, but we're adding a proton, which means there's the imbalance of electrons and protons. It's now a cation, ammonium ion. And now we are adding this in, and that's going to balance this out and end up being water. And here's a bigger definition about the number B, or letter B. So let's now identify the sets that contain acid-base conjugate pairs. So not all these are going to match up, and we need to make a definition. Remember, follow the hydrogen. Follow it, and we only do 1 hydrogen at a time. This one is a conjugate acid-base pair. This is the acid. This is the conjugate base, because you can see that the hydrogen is lost, and that ends up being a base. Here we have carbonate acid and carbonate. This is not a conjugate acid-base pair because we do not lose 2 hydrogens at once. We do them in steps, like what you would see here. And here we have HCl and ClO4 minus. They're not even related. This is not a conjugate acid-base pair. Here we have, on this side, let's start with this side, hydrosulfuric acid, and we have now a proton that has left this. So this means that if we're looking at this going forward, this gained a hydrogen, so this has to be a base and a conjugate acid. And then here we have ammonia and ammonium ion. It gained a hydrogen by definition for Brønsted Lowry. If it's a base, it gained. So here is the base and the conjugate acid. Okay. All right, so let's take a look at water and another compound, which is bicarbonate. In this middle, this is bicarbonate. This is carbonic acid. Here is water. Both of these can act as either, they can either take a hydrogen ion, or it can donate a hydrogen ion. And that has to do with what it reacts with. It depends on the other reactant, whether it's going to be acidic, behave as an acidic compound or a basic compound. And so let's take a look at it as water. Water donates a hydrogen ion when it reacts with a stronger base, because the base will take it. And water acts as a hydrogen, will accept a hydrogen ion when it reacts with a stronger acid. Let me see, donates base. Yes, I want to make sure I'm saying that right. Okay, so yes, I am. Remember, if it's in the presence of a stronger acids completely dissociate 100% like HCl. So it's going to be H plus and Cl. So the H plus is immediately going to go with the water because it's a stronger acid, dissociates 100% into ions. So here we have water and bicarbonate, and you can see what happens if it acts like a base. And you can see what happens if it acts like an acid. And this means amphoteric or amphiprotic is what these substances are. They can act, most substances cannot do that. They can either act as one or the other. These substances can act as both. So here, let's identify the conjugate acid-base pairs in the following reaction. First thing you should do, look it over, pick one compound and follow the hydrogen in it. So this one wants you to look at nitric acid. So we can see we have nitric acid on this side. Plus it's already shown here, but let's pretend that's not there. And let's follow it. And we can see in the forward reaction, it lost the hydrogen. So this must be the acid. This is the conjugate base. If this is the acid, this has to be base. Let's confirm it. It should have a hydrogen. It does. So this is the base, and this is the conjugate acid. So I've already kind of went a step ahead, but you can see the ammonia is the base, and ammonium ion is its conjugate acid because it takes the hydrogen based on the Brønsted-Lowry definition, and the acid loses that hydrogen ion. And you can see this is the acid and the conjugate base. Now it's asking to write them out. How do you write them out? Use a slash. So this one's asking specifically for the acid and the conjugate base pair. You should be very careful. If it's just asking for acid and base conjugate pair, then you can write whichever one first. But if it's specifically asking for the acid and conjugate base pair, then you need to make sure you write nitric acid / nitrate. And here's the base. You need to write ammonia / ammonium ion. And that's it.